Yeah. So, good evening, everyone. This is the NPTEL problem solving session for the course Introduction to Robotics. And this is the session for week 12, the last week of this course. So, in this week, I think you have learned about, path learning algorithms, majorly. Okay, and some basic localization methods, but majorly you have learned about path learning algorithms. And like since you guys have already covered much of the robotics introductory robotics in your previous weeks, so I think if you have any doubts in any of those materials, I would like to take that as well today, and if not, then I will just discuss some questions related to this week's material, and then we can either you can discuss your doubts and or we can end discussion. Pranav, can you hear me? Okay. Well, so I will start with questions then. Okay, so let us just take the first question. Okay, because most part in this week before the path learning algorithms, like when you discuss Dijkstra, BFS, DFS, or Eastern algorithm, was theoretical. Because I had some theoretical questions that are similar to what you get in your assignments. Okay, so I've asked you that which of the following can be used for position tracking. Okay, so if you remember the week from in which you learned about Kalman filters, essentially more filters, Kalman filter, EKF, particle filter, and all. Okay, there you learned like we used Kalman filter for you know state tracking. Okay, basically we used Kalman filter to estimate the mean position. Okay, and the variance in that position. Okay, so we used Kalman filter for that. So essentially, since position is a continuous variable, okay, and we were using Kalman filter to iteratively update this. Okay, so it is essentially a state estimation or position tracking algorithm. Okay, and EKF we had seen that you know so okay, so Kalman filter was for state estimation, assuming all the random variables are Gaussian. Okay, what do you mean by Gaussian? Okay, they follow non like Gaussian distribution with some mean and some variance. Okay, so Kalman filter assumes linear time, you know, linear systems essentially. You do not need them to be time invariant. Okay, linear systems with Gaussian, um, you know, Gaussian randomness or Gaussian noise, you can say. Okay, and extended Kalman filters, EKF. Okay, it was exactly Kalman filter, but for non-linear systems. Okay, so what we were doing, we were linearizing this non-linear systems for our
Sir,
yes, Pranav.
sir, can you give an example of non-linear system, sir? And I don't understand the difference between them.
Oh, yeah, sure. Were you there in the last week's lecture?
No, sir.
Okay. Have you seen this kind of system? Okay, a linear system. Have you ever seen this one?
Actually, I saw this in the recorded video, sir.
Okay, so are you asking that where do you see in real life a linear or
Yes,
non-linear system? Yeah.
yes, sir.
Okay.
Yes, sir.
Yeah, sure. So you know about drones, right?
Yes, sir.
Okay. So if you let's say you see whenever you are talking about a system, you want to talk about the state of a system. Okay. So let us say for drone, what can be the state? Okay. I can write the global XYZ position, okay, as three states, and then I can write the, let's say, three parameters that represent orientation. Okay, so I can say that this, along with their rate of change, okay, they describe completely the behavior of the robot. Can I say that?
Sir, the position and orientation and the rate of change, sir.
Yes, right.
Yes, sir.
I mean that if I have both of these informations, I can predict what the next state will be. Okay.
Yes, sir.
So now when you use these states and when you try to write the equation of motion, okay, for drones, okay, let us say this x dot is my whole vector. Okay. So what you get is an equation like this. Okay.
Two
So this,
functions.
yes. So this x here, okay, this f here is just a function of x and it is a non-linear function. Okay. Like if you want to know exactly what this f is for a drone, you can either, you know, try to derive the equations, or you can,
Non-linear function means the degree is greater than 1. Yes,
yes,
sir.
okay. So a non-linear functions means that, in f of x, there will be terms like x times y times cosine of, let's say, theta, okay, or cosine, cos theta, cos psi. Okay, so basically this function is not linear in x. Okay, what does it mean for a function to be linear in x?
Degree is 1.
Yeah, degree is one. Basically, all the terms related to the independent variable in the expression of that functions have a degree one. Okay, so even the trigonometric functions are non-linear.
Yes,
Okay,
sir.
let me give a very simple example actually. Okay, I mean, drone, you can see equations online, or you can even try to derive them. It is not that difficult. You know about a pendulum, right? A simple pendulum. Okay, so
Yes, sir.
yeah. Do you remember what are the equation of motion for a simple pendulum? Okay, simple pendulum with a mass m. Okay, and there is the angle from vertical I've taken is theta. Okay, and there is gravity acting downwards. Yeah. Do you remember what is the equation of motion?
Yes, sir.
Yeah, tell me.
Sir, for a simple pendulum, the force will act on the downwards and in the horizontal plane.
Yes. Yes. Okay, so like I think if I write, you'll remember. Okay, so the equation of motion for a simple pendulum comes out to be this, right?
Yes, sir.
Right? Because see, this angle is theta. Okay, this force is mg. Okay, and the component of this force perpendicular to this pendulum is the only restoring force that we have. Okay, the other component is only balancing out the tension, right?
Yes, sir.
So m theta double dot can be written as the moment due to mg. And what is the moment due to mg? If I say that the length is L, okay, that is mg sine theta in the minus direction times L, right? This is the moment due to mg sine theta.
Sir, what is theta? What is theta double dot?
It is the acceleration, angular acceleration of theta.
Okay, sir.
Uh, can I know, like, what background do you have? Are you a college student?
Actually, my first year starts the end of this month.
Okay, okay. So I think then you have done high school, right? 12th standard.
Yes, sir.
Okay, then I think you might have seen theta double dot as replaced by alpha. Okay,
Yes, sir.
the
There
angular
is alpha.
acceleration. Okay, so this alpha I'm writing as in place of d2 theta by dt square. Okay, and okay, now I see where the confusion is. Actually, when you go in college, you'll see this notation that when you write a dot of any quantity, okay, that just means one time differentiation with respect to
The
time.
first derivative.
Yeah, first with
Okay.
derivative with respect to time. Okay,
Okay.
and
Yes, sir.
yeah, and two dots means the second derivative with respect to time. Okay, so
Yes,
now
sir.
Okay, if you take this guy here, you know cancel out him, you'll get this equation. Okay,
Okay, sir.
okay, and now I define my state vector for the pendulum as theta and theta dot. Okay, because if I know theta and theta dot, I can predict what the next theta will be,
Yes, sir.
right? So now if I want to write, okay, in very general form, any equation of motion can be written in this form, okay, in form of the first derivative. Okay, this
Yes,
is
sir.
the general equation of motion. Okay, now if I want to write this, in terms of first order, because right now it is second order derivative.
Yes, sir.
Okay, so let us say I introduce a variable called v, okay, and I call it theta dot, okay, and then I write
V is
v
angular
dot.
velocity, right?
Yes, v is the. I've just this is just a substitution. You could have written here a also, anything. Okay,
Yes, sir.
and this v dot here. Okay, this becomes what? This.
Theta double
Okay,
dot.
yeah. So theta, but I don't want double dots. Okay, so what is actually theta double dot? It is this minus g over l sine theta.
Yes, sir.
Okay, so now you see, I can write this equation here as theta dot of this whole term. Okay, because this is my x. Okay, and in the right hand side, I can write v. Okay, theta dot you can replace with v also. Okay, minus g over l sine theta. Okay, so you see, this now becomes your x dot. Okay, and this becomes your f of x.
Yes, sir.
Is it fine?
Yes, sir.
Okay, now you see, right now there was no external torque or moment that I was applying at this point on this pendulum, right? If I say that I'm applying some external torque also on this pendulum, okay, and I'm saying that this torque is my control input, okay. So how does this change my equation here? Okay, so instead of 0, there will be a tau here, right?
Yes.
Okay, and how does this change further? There will be some plus tau term here, right? And
Yes, sir.
when I want to write it in matrix form, okay, and since I want to separate out my control,
Sir, isn't it tau by m?
huh? Yes, yes,
Tau by
sorry,
m.
yes, yes, my mistake. It will be tau by m. Okay, this is tau by m. Okay, so now you can either expand this itself, okay, to be called f of x comma, you know, I will say, generally control input is represented by u. Okay, so I say that my u is tau. Okay, just for the sake of convention.
Yes,
So
sir.
this equation now here is of this general form that we have been seeing. Okay, but
Yes, sir.
okay, but there is one more structure here to the problem. Okay, you can see this whole term, it is linear, non-linear in theta. Okay, that is why it is non-linear in x, but it is linear in my control, right? Because the maximum power of control is 1,
Yes, sir.
right? So I can
Yes.
actually separate these two, okay, as this v minus g over l sine sine theta, okay, plus, okay, some matrix times tau. Now, can you see that this equation and what we had written here, these are exactly the same,
Yes, sir. I understand, sir.
right? Tau, and then here 1 over m, right? Now these are the same.
Yes, sir.
Okay, so now this is, let us say, I call it f1 of x plus some matrix G times U. Okay, so now this is another form in which I can write my equation of motions for the simple pendulum, where F1 of x is this,
Yes, sir.
right? So this is the general nonlinear form, okay, that we see, and this form is called the control affine form. Okay, affine just means it is linear, and control affine means that it is linear in control.
Yes, sir.
Okay, so now if you try to write equation of motion for a drone also, they will also come in the exact same form. Okay, the form will be same. Okay, G U. Okay, this F might be different and this G might be different, but when you write it, condensed like this, okay, it will be in the same control affine form. Okay, it comes out like this.
Yes, sir.
Okay, so this is what we mean when we say that a system is nonlinear. Okay,
Non-linear.
right? And if this f of x is also linear, okay, and how do
Yes.
we make it linear? Okay, can you tell me what happens to the equation? Can I erase all this?
Yes, sir.
Right? So can you tell me what happens when I say that the you know angle is and angle of oscillation is very small?
Um, G by L sin theta will approach 0.
No, sine theta when theta is very small does not approach zero.
As theta approach 0, sin theta approach 0, right, sir?
No, no. See, do you know the expansion for sine theta?
No,
Yes.
sir.
No? Okay. Yeah. Do you know what a Taylor series is?
No, sir. I don't. I haven't seen this, sir.
Okay. I think you might be getting confused with the names only. Okay. We can write sine theta or sine of, okay, sine theta is theta plus, no, no, not plus. Um, Here, minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial. Okay. And so on. Do you know we can write sine theta like this?
Yes, sir. I've seen this series, sir.
Right. So like this comes from Taylor series expansion. Okay, or there are other methods of getting also, but the point is now let us say that theta is very small. Okay, whenever we say that something is very small, we want to say that the effect of higher powers is negligible.
Yeah. Yes, sir. Now I remember. Sin theta approach theta.
Yes. Okay, when theta is very small, sine theta approaches theta. Okay, so now this equation of motion of mine that I was writing, okay, this becomes V as the same theta dot. Okay, but this V dot, okay, what does it become? Minus G over L theta plus tau over M, right? Now see,
Yes, sir.
both these equations are linear in my states, okay, both in theta and theta dot. Okay, so if
Yes.
I go to write it in the matrix form, okay, this will become x dot because this is theta dot, or you can write V dot, okay, and here it becomes 0 1 minus G over L 0. Okay, and this is my x. Okay, I'm just writing theta and theta dot here, but this is actually my x plus 0 1 over m tau. Okay, so you see now this is of this form. Okay, x dot is equal to ax plus bu, right?
Yes, sir.
Okay, and you got right how I wrote
Yes, sir.
this
I got
from
it,
the,
sir.
right. So now this is completely linear. Okay, so this is the linear form. Okay, this is a
Yes, sir.
linear system, right? Okay, and there are different types of linear system. This is a linear time invariant system. Okay, essentially this A and B, okay, these depend on my system, right?
Yes, sir.
Okay, like how much gravity is, what is the length of the pendulum, they do not change here. Okay, so that is why we say that it is a time invariant system. If this A and B could change with time, okay, then we
It
call it a
becomes
linear.
non-linear.
No, it is still linear. Okay, linear and non-linear depends on the states. Okay,
It changes with time means it won't it become non-linear, sir?
no. See, non-linear, you said, right? It has to be just of the first order.
Yes, sir.
Okay, so even if A and B change, but it is still, the order of X is still one, right here.
If
If I
even if
say,
a and b change, it should not be the function of x. That's what you're saying, right,
yeah,
sir?
A and B, of course, should not be functions of X. Okay, I'm saying that A and B are just functions of time. Let us say that I say this L length here is changing with time.
Yes, sir.
Okay, then this A has now become a function of time. It will change with time,
Yes, sir.
right? But at every time, it will still be only linear in X,
Yes, sir. That's correct, sir.
right? So that is why when A and B both change in time, then it is called a linear time varying system. Okay, so even linear systems are of two types. Okay, I think what engineering major are you taking, or like what are you
Mechanical,
going
sir.
to mechanical? Okay,
Yes, sir.
then I think you might not come across this, depending on if your college teaches you control systems or not. But this is like basics of control systems. Okay,
Yes,
that
sir.
what kind of system it is. Okay, and how can we convert a non-linear system into a linear system. Okay, did you see, essentially we linearized this non-linear system into a linear system. How did we
By
linearize?
reducing the value of theta.
Yes, okay, by linearizing the non-linear part. Okay, so when you have seen lectures on Kalman filter, right?
Yes, sir. I have seen, sir.
Were you able to understand them?
And I understood a bit, sir.
Okay, so I actually have uploaded like some time ago a lecture on week 10, I guess. Okay, in that I have explored how we actually derive the five equations for Kalman filter. Okay,
Yes, sir.
so essentially there you will see. Okay, so in Kalman filter, the original Kalman filter algorithm, we assume that our systems are linear. Okay, and whatever the noise in the system is, okay, that noise we assume to be Gaussian. Okay, here we say that this WT has zero mean and let us say PT variance. You know what is mean and variance?
I've heard of it, sir, but I'm not sure about it.
Um, okay, I think you might have heard. Do you know about standard deviation?
Yes, sir. I know that, sir.
Right. So I think in probability you might have learnt about mean of any given data, the standard deviation of any data, right? So how do we calculate standard deviation? Okay, standard deviation is just the square root of variance. Okay, so essentially this is the same variance we're talking about, but in matrix form. Okay, so
Okay, sir.
you don't need to think much about it for now. Okay, because you will learn linear algebra in a much greater detail once you join college. Okay, but uh, to understand
Sir.
robotics well, okay, and to understand filters well, you should be comfortable with the notion of probability. Okay, and comfort. Yeah, you
Yes,
were
sir.
saying something.
Sir, no, sir. No, sir.
Okay, so essentially, for the original Kalman filters, we assume that our system is linear and all the randomness is Gaussian. Okay, for extended Kalman filters, okay, we extended Kalman filters were made for non-linear systems like this. Okay, but what we do here is we
Extended
linear.
Kalman filter won't work for linear, sir.
No, it can work for linear. Okay, see, it's not like you make Kalman filter to work for linear systems. Okay, you have a linear system. Now you want to make a filter for it. Okay, so extended Kalman filter. Okay, because see, if the system is
Okay.
non-linear, the original Kalman filter cannot work. Okay, so you modify this original Kalman filter such that it can handle the non-linearities as well. Okay, and since it can handle non-linearities, it can work for linear systems as well. Did
Yes,
you
sir. I
understand?
understand, sir.
Okay, so essentially what we do
I
is,
understand, sir. I getting it.
yeah, we linearize the non-linear system. Okay, like we did here. Okay, this was the non-linear system. We linearized it like this. Okay, and there are different steps in a Kalman filter algorithm. Okay, do you know?
Sir, can you
Like
repeat, sir?
I'm not asking the steps, but right? There are multiple steps in Kalman filter algorithm.
Yes, right, sir. I know, sir.
Okay, so wherever you want to do this variance update, okay, there you use the linearized version. Okay, and wherever you do the mean update, most of the time you use the non-linear version. Okay, so that is the only difference between Kalman and extended Kalman filters. Okay, extended Kalman filters are
Uh,
basically Kalman filters extended to work for nonlinear equation of motion,
yes, sir. I get it, sir.
right?
Yes, sir.
And then there is one more type of Kalman filter that I think you guys have not been told about. That is the UKF. Okay, that is unscented Kalman filter. Okay, so you will learn about UKF if you take any course on Kalman filtering, let's say, or navigation. Okay, so but I think since you will be joining as only a first year right now, so knowing just the names and if you can just understand how to use the Kalman filter, that will be more than enough for you.
Yes.
Okay. Yeah. So can you tell me the answer for this question, by the way?
Which of the following can be used for position tracking?
Yeah.
Mm, sir, is
Mhm.
it extended Kalman filter, sir?
Is it only extended Kalman filter?
Extended Kalman filter and particle filter, I think.
Okay. And why not Kalman filter or binary based filter?
Because Kalman filter won't work for non-linear system,
Yeah.
right?
But see, we have not been given, right, which kind of system there is. They're just using for any kind of system. Okay. Any system that you can give. It may be linear, non-linear. It is up to us. Can it do position tracking?
It can do position tracking, but only for linear.
Right? But it can do, right, position tracking. So, and why
Yes,
not
sir.
binary based filter?
I'm not familiar about binary based filter a lot.
Okay, I think it was there in week 10 lectures as well. Okay, so essentially what binary based filter gives us, okay, it gives us only binary output. Okay, let us say it will only tell us whether a door is open or it is closed. Okay, but for position tracking, we need a continuous variable, right? Uh, Let us say that this is a workspace of the robot. Okay, so my robot can be in any position in this entire workspace, right?
Yes, sir.
Okay, but my binary based filter can at best tell me that my robot exists or not. Okay, but it cannot track the position, right? Because it can only give you two states.
Yes, sir.
Okay, so that is why your binary based filter cannot, you know, give you position tracking. Okay, and yeah, all these three they can easily give you, position tracking.
Yes, sir.
So I think you will need quite a lot of reading before you're actually fluent and you actually do understand what we mean by all this. Okay, but I hope, have you watched all the lectures till now?
Not everything, sir. I have to watch the week 11 whole and then the week 12.
Okay, okay. Yeah, that's fine. Okay. So which part did you like the most, or you think that you kind of understand that part?
The first one, sir. The one which Ashokan sir took.
Okay, the robot kinematics and dynamics.
Yes, sir.
Hmm. Okay. But I think you guys are not done dynamics till now, right?
Sir.
You guys, like, he did not teach you dynamics, right? How to write equation of motions for a robot.
Yes, sir. Not it, sir.
Yeah. Do you know about Euler-Lagrange equations?
No, sir.
No. Okay, so you know only about Newton's equations, right? Newton's and Euler's equations.
Yes, sir. I know about Newton's equation.
Okay, I think in your third semester in engineering, you will learn about, more methods apart from Newton and Euler methods to write the equation of motion. One such method is the Euler-Lagrange equations.
In mechanical, will I learn that, sir?
Yes, yes, because in mechanical, it is very crucial to know the mechanics,
Yes, sir.
right? Yeah. So I think it will come as the subject called engineering mechanics,
Yes, sir.
right? So there you will learn about this approach.
Okay, sir. Sir, you are a student of IIT Madras, sir?
No, no, I'm a student of IIT Kanpur.
Okay, sir.
Which college are you joining?
Rajalakshmi Engineering College, sir.
It
That's in Tamil
is
Nadu.
in Tamil Nadu. Okay, that's good. Okay, so if you are interested in robotics, okay, what I would suggest you do is that you, apart from just taking these lectures, you actually try to build something.
Sir, try to?
Try to build something. Build a small machine.
Yes,
Okay,
sir.
try to get familiar with the hardware. Okay, and
Yes,
the
sir. Okay,
best
sir.
the best way that I have seen work, and that has also worked for me, is you try to look for robotics competitions, right?
Yes, sir. Yes, sir.
Okay, and you look for robotics competitions, and then you try to prepare a robot for that particular competition. Okay, and you know if you need any guidance related to that, do you know my email ID?
No, sir. May I take a note, sir?
Yeah, sure.
Yes, sir. Thank you, sir.
Yeah, so this is my email ID. You can contact me on this. Okay, if you in case you need any guidance. Okay,
Okay,
so
sir.
because the theory part of robotics, it takes some time to understand and get used to. Okay, but the hardware part is equally important. Okay, so
Actually, I plan to do my PG in robotics in automation.
oh, that's great.
Yes, sir.
Yeah, but see, still, to be better prepared for your PG. Okay, I would advise that you start robotics from an undergraduate itself,
Yes, sir.
right? And knowing hardware is a very crucial part of doing robotics,
Yes, sir.
right? Because see, the robotics, of course, you have studied also in this course, and you will get to know also in the upcoming time that robotics is where all kind of engineering combines, not just mechanical. Okay, mechanical, electrical, electronics, computer science, even sometimes biotech. Okay,
Yes, sir.
so for robotics, you actually need to know how systems work, and the best way to know how systems work is to work with them.
Okay,
Yes.
sir.
Yeah. So that would be my user advice. So have you seen path planning lectures? Or do you know anything about path planning?
Um, I'm not that familiar, sir.
Okay, then it's fine. I was just wondering if it would make any sense to go on for further questions. So, like, you can ask me any doubt if you have, or you can ask me any concept that you want me to explain. I can do that. Or if not, then I think we can wrap up this lecture.
Yes, sir. I have to see the remaining lectures of
Hmm.
the week 11 and week 12, so I don't think I can ask anything now.
Okay, like anything related to previous week's lectures also. If you have any doubt, you can ask. Like, if you do not understand anything in the motor control lectures, or what you should read more, you know, to know more about motor control, or even for dynamics, if you dynamics or kinematics, if you want any guidance, if you are facing any problem, right? Writing the DH table
As of
or
now, I don't have any doubt. If I have any doubt, can I email you, sir?
yeah, sure, sure, you can email. And
Yes, sir.
yeah. So I think we'll wrap up now.
Yes, sir.
Yeah. Thanks for attending.
Yes, sir. Thank you, sir.
Sure.